All right, that's Mr. McMurray back with Working Power Notes, and here we are. We've talked about some things require you to use machines can help you do work, make it easier for you. It can't change the amount of work you have to do. It takes the same amount of work to do something by hand as it does with a machine, but it can make it easier for us. And one of the ways we talked about is, say, with a broom, it takes more force to push it up here than it would to push it down here at the bottom, but we move our hand a small distance and it makes it move the machine moves a large distance. And since I don't want to sweep very much, that means I'll get through sweeping a lot faster. So we say it multiplies our distance. So I have to put in more force, a shorter distance, and it makes the broom exert a smaller force on the floor and goes a longer distance, and therefore I can sweep quicker. So it multiplies the distance, okay? That's only good for things that don't take much force. If it takes a lot of force already, we don't want a machine that causes us to use even more force usually. But if it's a small amount of force like a broom, that's a good idea. All right, now for a hammer, all right, we have a hammer, all right. I put in a small amount of force and I move the handle, say 6 inches, and we said the hammer puts force on a nail and only moves it about 1 inch. So if I move this 6 inches, I'm going a farther distance, but I'm using less force, and it's putting 6 times as much force, but going a bit smaller distance. So it's doing the same amount of work either way, but it's putting a lot more force on the nail, which is good for me because I don't want to have to use that much force, right? Okay, so anyhow, that's how the hammer works. It multiplies our force. We put a small amount of force in over a long distance, and it gets a large amount of force exerted on the nail or whatever we're trying to move for a short distance. All right. But since we don't have to put as much force in, it feels better for us. Okay. The last one we said, was we wanted to do a pulley. And I don't know if we just barely got to that. If you have a pulley like this, it's just a wheel basically with a little groove in it that you can put a rope or something so you can use it to pull things. All right. If you do this one by itself, what you're actually doing is changing the direction of the force, okay? Now, say I want to lift a bale of hay, okay? I have a bale of hay over here. I'm going to tie a rope around it and put it around the pulley, okay? So instead of lifting up, now when I lift up on the bale of hay, how much of the force do I have to supply to lift it? All of it, right? Because gravity's pushing it down, whatever its weight is, and I'm trying to push it up against that weight, okay? So I'm trying to lift that up against that weight, and I have to do all the work myself. But if I put it over a pulley, now if I just would take my feet off the ground and just yank, it would lift it. As long as it didn't weigh more than I did, it would lift whatever it was off the ground. Okay, and so I don't have to use very little, if any, force on my hands. I can just use my weight and gravity to help pull. So now I'm kind of pulling with gravity, and gravity acting on my body acts in my favor. Okay, and so this is changing the direction of the force, and therefore I don't have to supply all the force. Now gravity can work with me instead of against me. All right, and that's basically what that is. Now that's only true for one pulley. If you get more pulleys, it ends up being kind of like number 2, where, for example, if you have a car with an engine and you need to lift the engine up, you can hook it up to a block and tackle, which is a whole bunch of pulleys like this, and you can lift it. One person by themselves can lift it, even though they couldn't lift the engine, of course, obviously by themselves, the engine block. But it might, for example, though, you have to pull 10 feet of rope just to make the motor go up 1 foot. So once again, you're using less force, but over a longer distance, kind of like here on number 2. And so it's multiplying your force and allows you to pick up the big engine block you normally wouldn't. So right here, I don't have it written down, but if you'll put changes the direction of force, and this is true of single pulleys, and it allows gravity to work with you instead of against you. All right. All right. Now, so really, anytime you have a machine, there's 2 forces and distances going on. There's the force and the distance you put into the machine, like when I pull on the handle of the hammer, and there's the work that's actually done by the machine on the object that we're trying to move. Okay, now the force that I put there is called the effort force. Okay, so that's the force I apply to the machine. It's capital F for force and then E to show what kind. It's the effort force. It'd be better if his EF, people would remember it better, but that's just the way it is. Okay, now the distance I move the handle then would be the effort distance, because that's my effort. I'm putting effort into the machine, and so it's moving at a certain distance. Okay, so that's the distance I move it. Now, we have force and we have distance. If we multiply this force times the distance, the effort I put in and the distance I move it, then guess what? We find work, okay? But this is work input because I'm putting in work on the machine. All right, so I'm inputting work on the machine. So it's called work input, or win for short. Big W for work, and then IN for input. So win. So when you use a machine like this, all you're gonna do is win, win, win. Okay, you get the idea. Okay, all right. That's why I didn't become a singer. But anyhow, that's the amount of work that you do on the machine. Okay. Now the formula for that, then we said, is just work input is equal to the effort force times the effort distance. Okay, force times distance, work, can be measured in joules or newton meters, just like any other kind of work. All right. Now, the work the hammer does on the nail is not going along with this, it's resisting. So whatever the object is that's resisting being moved is called the resistance. And so this is called the resistance force. The force we put on the object to move it is called the resistance force. And depending on how much it resists, determines how much force we have to put on it to lift it up. So the resistance force is just the force applied by the machine on the object. Okay, so the force applied by the machine on the object. Right. So how much force this puts on, about 6 times as much force as I put on the handle, that's the resistance force. Now, the distance that I can move the object is called, very rhythmically, resistance distance. It rhymes, so we can be poetic if we want. Resistance distance, or dr. All right, and this is the distance that the machine, in this case the hammer moving the nail, moves the object. All right. And once again, if we do force times distance, guess what? We're going to have work. But this time, instead of work input, we put in work to it. The machine has work that it puts out. So this is the work output, or wout. Okay, so you can win or you can wout. You win, the machine wouts. It puts work out on the object. So the work done by the machine on the object is called the work output. Okay? And work output is equal then to the resistance force times the resistance distance. Now, in relatively speaking, these two need to be about the same. You put about work in. But technically, some of the work you put in here probably gets lost to resistance and friction and stuff like that. So actually well, that's a good question. I think I'll ask you that on the quiz. Which one is going to be more or less, work input or work output? All right. And that's all we're going to do for this recording. All right, I had one earlier, but it did not have volume, so hopefully this time everybody will hear it with volume. And we will see you tomorrow.